Welcome. Today we will discuss vector control of AC machines. That is induction motor vector control we will discuss. So, why the name is vector control, the other one is scalar control. In previous classes, we discussed about scalar control of induction motor at length. Scalar control includes control of voltage fed inverter fed induction motor drive, current inverter fed induction motor drive, and other scalar control techniques like rotor resistance control, slip power control. Those are the scalar control techniques, because those were not they didn't use vector approach. In vector control induction motor drive, in those scalar control induction motor drive, the problem was the transient response was sluggish. Why? Because the torque and flux are coupled, they are not independent of each other. So, torque and flux are coupled. When due to that the response is sluggish, and also it makes the drive unstable, because induction motor model is a fifth order model. As we discussed in previous class, there are 4 state variables, electrical variables, and there is also torque equation. So, system matrix is 4 by 4 and there is a torque equation. So, induction motor model is a fifth order model, and because of coupling between torque and dependence between the torque and flux, the drive response is sluggish, and sometimes it is prone to instability. So, for that was the main demerit of scalar control. And with an example you can see, suppose the speed is to be increased, that means torque is to be increased. So, that means slip and frequency are increased, slip is increased, that means frequency is increased. So, when frequency is increased, it tends to decrease the flux, and when flux decreases, the response becomes sluggish, because flux response is sluggish, flux time constant is larger, field time constant is larger. So, flux response is sluggish. So, the overall response becomes sluggish. To compensate the decrease in the decrement in the flux, a flux compensation loop is used in the voltage control. So, that again it makes the system more complex, and also it is again a sluggish. So, this way the performance of the scalar control techniques are not satisfactory, or not very well appreciated. So, for that led to development of vector control of induction motor. In vector control of induction motor, the induction motor is controlled like a separately excited DC motor. That means, in the flux and torque are controlled independent of each other, and where fast response is obtained, fast transient response is obtained. The vector control was developed in 1970s, and because torque and flux are decoupled of each other, decoupled from each other, this is also known as decoupling control or orthogonal control or trace vector control or simply vector control or field orientation control. Those are developed in 1970s, and that gave very good performance, fast transient response, and for that they have replaced the classical scalar control techniques of AC drive, and also the high performance DC drives also are replaced by these high performance vector control induction motor drives. So, let us understand how the vector control induction motor drive can give the performance of separately excited DC motor drive. So, first we will go to DC motor drive analogy. So, first we will draw the DC motor. So, this is the field which carries the current I f, field current is I f, and armature I a, armature carries the current I a. As you know, armature current, armature winding, the distributed armature winding is equivalent to unwinding, concentrated winding between the brushes. So, when the armature winding carries the current, it produces the armature flux, flux linkage psi A, which is produced by the armature current I A. That is, the armature flux is in the same along the brush axis direction, because it is winding, armature winding is between the brushes, and field winding is at right angle to the brush axis. So, this is the axis of the field flux I f, which is produced by the field current I f. So, this is the space phasor diagram, space vector diagram. In DC motor, by construction, the brushes are at right angle with the field poles. So, brush axis and field axis are at 90 degree to each other. So, because armature winding is equivalent to a concentrated winding between the brushes, the armature MMF and field MMF, they are at 90 degree to each other by construction. So, because they are at 90 degree to each other, when the armature current is controlled to vary the torque, the field flux is not affected. When the field current is controlled to control the field flux, the armature MMF is not affected. So, armature flux and field flux are mutually decoupled from each other. There are no dependence between one another. They are totally independent of each other. Variation of armature current does not affect the field flux, and variation of the field current or flux does not affect the armature flux. So, they are mutually decoupled or orthogonal to each other. Due to that reason, the torque, electromagnetic torque T E, which is proportional to field flux and armature current, that is K T psi f into I A, or you can write K T dash into I f into I A. Psi f is proportional to field current I f by neglecting the saturation. So, you can see, because field flux and armature flux are right angle to each other, orthogonal to each other, the transient, because of this inherent decoupling, transient response is very fast. And also, by speed is controlled below the rated speed by armature control technique. By varying the armature current alone, field flux is maintained constant at the rated value, that gives the highest torque to current ratio, that is highest torque sensitivity. And above the rated speed, field weakening control is done and field flux is reduced to give high speed operation, and during that time also torque sensitivity is good, and also response is fast response during flux weakening control. So, due to these advantages, DC motor was preferred for all the industrial drives requiring high performance application, high performance drives, because of this fast transient response and all these advantages. But DC motor has the problem, as you know, the maintenance, the commutator and brushes, they require frequent maintenance, and all the frequent maintenance, and this commutation problem is the main one problem, and good commutation is difficult, it sometimes becomes a problem to achieve good commutation. And from this point of view, induction motor is better, but induction motor has the problem, the coupling, you do not get this type of coupling in induction motor. In induction motor, torque Te is proportional to flux, say psi r hat rotor flux, into current, rotor current I 2. And when rotor current is changed, it affects the air gap flux and hence it affects the rotor induction and rotor current. So, there is a coupling. To eliminate that coupling in vector controlled induction motor drive, to get the DC motor like performance, we use a vector controller like this, a vector controller at the front end, feeding an inverter, and this inverter feeds the induction motor. So, this is the vector controlled induction motor scheme. In vector control induction motor, at the front we have two command currents, one is IDS star reference value and IQS star. So, these are the command current components. For this vector control induction motor drive, now the torque equation becomes torque Te is proportionality constant Kt into psi r hat psi r peak into IQS, and that is Kt dash some other proportionality constant into IDS into IQS for the vector controlled induction motor drive. In this vector controlled induction motor drive, this IDS and IQS are their star value. IDS and IQS are the D and Q axis components of stator current. So, as I have mentioned D and Q axis components, so we have considered a synchronously rotating reference frame which has to be there. So, we consider the induction motor in a synchronous rotating reference frame, and in this synchronously rotating reference frame, the IQS is called the torque component of current, or stator current, which is equivalent to armature current IA of DC motor, and IDS is the flux component of current equivalent to field current of DC motor. So, what I have written, IQS is equivalent to IA and IDS is equivalent to IF of DC motor. So, now in this synchronous rotating reference frame with the vector control, when we get this torque equation, in this torque equation this IDS and IQS are independent of each other. When torque is to be controlled by controlling the q axis component of the stator current IQS, the flux psi r remains unaffected. Flux psi r remains unaffected. And when for high speed operation flux weakening control is done, flux is controlled by controlling the d axis component of the stator current IDS, and during that time the torque component of the current IQS remains unaffected. So, IDS and IQS are mutually decoupled from each other, are orthogonal to each other, and for that reason we get very fast response in vector controlled induction motor drive, just same as or better than the DC separately stated DC motor. So, we have here in phasor diagram, we have here flux psi r and IQS, they are in phase, and IDS sorry IDS and psi r are in phase, that is the flux and flux component of the current are in phase, and they are at right angle to torque component of the current IQS. So, they are mutually orthogonal, so that we get fast transient response like DC motor, and for that reason the vector controlled DC motor drive, vector controlled induction drive is preferred. This is the stator current IS, which is phasor sum of IDS and IQS, and fast transient response is obtained because these are mutually decoupled. And for that we have to consider a synchronous reference frame and control the induction motor using a vector controller. The vector controller at the front end has two command inputs, the flux component command IDS star and torque component of the current command IQS star. When flux is to be controlled, the IDS star is varied, IQS star is kept constant, and IDS star variation varies only the IDS, affects controls only the IDS, and IQS remains unaffected. And when control is to be done at constant flux, IDS star is maintained constant and IQS star is controlled, and that affects only the q axis stator current IQS without affecting the flux. So, that fast transient response is obtained and decoupling is obtained. So, the torque expression is torque expression is similar to DC motor like DC motor expression, and particularly vector control. In vector control induction motor drive, this space phasor which we have just drawn, they are at right angle to each other, flux phasor and current phasor, they are at right angle to each other, and but they are rotating at synchronous speed. But in DC motor, the field flux phasor and armature current vectors, armature current space vectors, they are 90° apart, but they are stationary. In AC machines, they rotate at synchronous speed omega e. So, when we consider the synchronous rotating reference frame, they appear as DC quantities. In synchronous rotating reference frame, the sinusoidal motor quantity variables appear as DC quantities. So, the space phasor, space vector which is rotating physically from reference frame appear as DC quantities. So, it is possible to control the induction motor like a DC motor and to get DC motor like performance, fast transient response and decoupling and high torque sensitivity. So, these are obtained, but for that we require feedback signal processing with, and that also sometimes we require estimation for sensorless vector control. So, for high performance vector control, digital signal processing is required, DSP is required, and with DSP and with this vector control DC drives have replaced the classical DC drives, and vector control is also applicable to induction motor as well as synchronous motor in the same principle. Okay. Next, let us consider the equivalent circuit and phasor diagram. Previous diagrams were space phasor diagrams, space vector diagrams, but now we will draw the phasor diagram. So, first we will draw the equivalent circuit. We have the stator resistance R S, stator leakage inductance L S, mutual inductance L M between stator and rotor, and we neglect the rotor leakage reactance. Just for understanding, for the time being. So, if we neglect the rotor leakage inductance in the rotor branch, we have only the resistance R2 dash by S. Applied voltage is Vs phasor, and voltage after from Vs phasor after the stator resistance drop, we have the phasor Vm across the field inductance. So, because rotor leakage inductance is neglected, psi R phasor equals to air gap flux phasor psi m, because there is no rotor leakage. So, that is the thing, and this is the current IDS which produces the flux flowing in the inductance Lm. So, Lm is the main inductance which produces the air gap flux, making the power transform possible. So, it is the field component IDS, field component of the current, and the rotor current, rotor branch current is now in phase with Vm, and we will write it is at 90 degree to IDS. So, we will write that IQS. Because rotor branch is purely resistive and mutual inductance is purely inductive, the current between the inductance, mutual inductance and rotor branch, they are at 90 degree to each other. So, because current flowing in the magnetizing branch is Lm, that is the field component of the current IDS, the other component rotor current is IQS, because it is at right angle. So, now let us draw the phasor diagram. This is the phasor Vm across the magnetizing branch. Now, current IQS is in phase with Vm, because rotor branch is purely resistive, and psi m, which is also same as psi r, they are at 90 degree behind the Vm, and IDS is the current, that is also 90 degree behind Vm, IDS. Now, phasor sum of IDS is the flux component of the current, because it is in phase with the flux. So, it controls the flux only, and IQS does not have contribution to flux. So, it is the torque component of the current, and phasor sum of IDS and IQS is the stator current IS. And phasor voltage Vs is at a certain angle with Vm, because stator impedance drop is there. So, now suppose flux is to be reduced to give high speed operation. So, if flux is reduced at a constant torque component of current IQS, like this flux is reduced to new value IDS 2, IQS remains constant. So, new value of stator current is now IS 2, like this. If keeping the flux component of the current, the torque component of the current is reduced to IQS 3, keeping the flux component of the current constant, then the new value of the stator current is IS 3 as shown here. So, what you see, we control the magnitude of the stator current as well as the phasor diagram. As you see, initially for one value of torque and flux, we get IS, which has a angle theta with voltage Vm, and when we change the flux component of the current reduced, the current changed to IDS 2. So, its angle changes to theta 2, and when we changed the torque component of the current, its angle changed to theta 3. So, we control the magnitude of the current as well as the phase. So, we control the current as a vector. As you can see, the magnitude of the current and its position angle is changed, the tip of the vector changes, moves. So, that is why it is called vector control. Hence, the name is vector control, because in conventional methods of induction motor control, we control only the current. When we change the applied voltage or frequency, the magnitude of the current changes. We control the magnitude of the current, but we do not change the phase angle of the current. An alternate AC quantity has both magnitude and phase. In vector control, we control the magnitude and phase of the current, so that we control the current as a vector or phasor. hence its name is vector control. And most important, when we change, and current has two components, one is direct axis component stator current component IDS, and quadrature axis stator current components IQS. They are mutually orthogonal and decoupled from each other. So, when one is changed, IDS is changed, IQS remains unaffected. When IQS is changed, IDS remains unaffected, due to which DC machine like fast transient response is obtained to give a high performance drive. So, this is one which is demonstrated using by neglecting the rotor leakage inductance, but while considering the rotor leakage inductance also, the control can be implemented to give the decoupling between the flux component of the current and torque component of the current, and to obtain mutual orthogonality between these two components, so that to get fast transient response. The stator current IS hat has two orthogonal components, IDS, which is the magnetizing component, or flux component, or reactive component of stator current. Flowing through the magnetizing inductance LM. The IQS is the torque component or active or in phase component of stator current flowing in the rotor circuit. So, stator current IS is square root of IDS square plus IQS square. IQS are the active component contributes to the active power across the air gap. So, it is the active component. and the reactive or flux component IDS contributes only reactive power. So, the main point of vector control is IDS and IQS components of stator current IS are controlled independently with control of one making no effect on the other. So, this is in Cartesian coordinates. In polar coordinates, stator current IS has the magnitude IS magnitude and a phase angle theta. The magnitude and phase of the stator current are controlled giving the name or justifying the name vector control. Means current is controlled like a vector, its magnitude and phase both are controlled, hence the name is vector control. In scalar control techniques, only the current magnitude is controlled, phase angle is not controlled, hence the name is scalar control, and here it is vector control because both magnitude and phase are controlled. So, current is controlled like a vector. So, now the point is when the flux component IDS is controlled, it has no effect on IQS. So, only flux is controlled, IDS controls the flux, no effects on IQS. And when IQS is controlled, it controls the torque, but no effect on flux, or IDS. Then how this is achieved? That is the technique of vector control which we are going to discuss now. So, we will discuss the principle of vector control. So, we have a block from dq to 2 phase. 2 phase means alpha beta transformation. So, we give the command value of the flux component of the current IDA star and command value of the torque component of the current IQA star. These are the reference values for the flux and torque component of the current, and this transformation block takes the unit vector, that is cos theta E and sin theta E. This unit vector is essential, and this is performing the action which is called vector rotation. This vector rotation block converts the DC quantities to 2 phase components in alpha beta frame. Those are I alpha A star and I beta A star. These are 2 phase currents in alpha beta frame. So, now we have a block from 2 phase alpha beta to 3 phase transformation. So, this 2 phase to 3 phase transformation, this converts the command currents to 3 phase current commands IA star, IB star and IC star. These are the 3 phase current commands. So, these are the inputs to the inverter terminal, inverter control. So, this action is the control action, what we have discussed, control action or the main vector control action, you can say. This is the control action, and this part is the, this action is the inverse transformation. In this inverse transformation, the control commands ID flux component and torque component current commands IDA star and IQ star are converted to 2 phase command currents using unit vector e to the power j theta E, and then from 2 phase to 3 phase current commands I star, IB star, IC star current commands and given to the inverter, and inverter is not shown in this figure. So, the current inverter feeds the same current to the motor. The currents are IA, IB, IC. Instantly it feeds the same current. So, these 3 phase current commands which are input to the motor machine, these are first converted from 3 phase to 2 phase alpha beta transformation. This is a transformation occurring in the machine. IA, IB, IC are the currents fed by the inverter to the motor. Inside the motor, we assume it is transformed from 3 phase to 2 phase alpha beta. And then after this 3 phase to 2 phase transformation, this gives I alpha S star, I alpha S and I beta S and this is from alpha 2 phase alpha beta to dq transformation occurs. For that, it takes the unit vector cos theta e and sin theta e, and it feeds to the machine dq model. It feeds the current IDS and IQS. So, machine model is in DQ synchronously rotating DQ frame. So, we have the current IQS of the motor and IDS of the motor at right angle to each other, and these reference frames are rotating at speed omega e. And this is the machine terminal. And this part is the transformation occurring within the machine. This is for modeling the motor in the frame, so that we can control in the vector control way. So, this is also the vector rotation block. So, we have the inverse transformation, which converts the reference current commands IDA star and IQ star to two phase current commands I alpha star, I beta star using the unit vector, and then from two phase to three phase current commands I star, IB star, IC star, the three phase current commands to the inverter. And what we assume? We assume inverter has unity gain and no time delay, instantaneous response. So, that means inverter gives IA star, IA equals to IA star instantly, IB equals to IB star instantly, IC equal to IC star instantly. So, inverter is not shown here, inverter is shown as just a border. So, inverter instantly feeds the same current IA, IB, IC equal to the reference values, command values I star, IB star, IC star to the motor. Inside the motor, we consider the motor model in DQ frame. So, it has two current components IDS and IQS orthogonal to each other, and motor rotating at the reference frame rotating at synchronous speed. And so, inside that what happens, this transformation from 3 phase to 2 phase transformation, then from 2 phase to 3 phase transformation occurring through vector rotation using the unit vector, and IDS and IQS are the machine currents. And this is also another thing, this is the flux psi r hat. So, that IDS is aligned along the rotor flux psi r. The flux component of the stator current IDS is aligned along the rotor flux psi r. So, this is the vector orientation. So, in the motor, the internal conversions occurs from 3 phase to 2 phase alpha beta and then to DQ model internal conversions occur. These are occur, which are the transformations. So, main point is this unit vector which is given by e to power j theta e, magnitude is 1 and angle is theta e. It has two Cartesian components cos theta e plus j sin theta e. This unit vector assures the correct alignment of flux component of current IDS with flux vector psi r hat. The torque component of the current IQS is oriented at 90 degree to flux vector psi r hat. So, this is ensured by the unit vector, this orientation of the flux component of the current IDS with the flux vector psi r. This orientation is assured by the unit vector and torque component is oriented 90 degree to the flux vector. This is the vector orientation and that is achieved by unit vector. So, this unit vector is most crucial for vector control because it unit vector only ensures that the flux component of the current IDS is aligned along the flux vector in the same direction as the flux vector and torque component of the current IQS is oriented at is perpendicular to the flux vector psi r. So, with that, when the flux is to be controlled only, then IDS star is controlled to control motor current IDS and hence flux psi r hat. IDS star is coming from the control block, it is the reference command, it is the control block. So, the command current IDS star is controlled to control the motor current IDS and hence the flux phi r. It has no effect on IQS. So, this is for high speed operation, the flux control is done, field weakening control is done, and for speed operation below the rated speed, the torque control is done. So, IQS star is controlled to control motor torque through IQS IQ star is controlled to control the motor torque through IQS. During that process, flux psi r hat and IDS are constant at rated value. This is for speed control below the rated speed. So, effect of one has no control of variation of one has no effect on the other. So, all the time IDS equal to IDS star and IQS equals to IQS star reference values. This transformation which we do, first inverse transformation from IDS star IQS star to IA star IB star IC star, and the transformation from IA IB IC to IDS IQS. This transformation and inverse transformation do not take any time. So, there is no dynamics involved. So, in a response is instantaneous. That is the main response is instantaneous. So, inverter has no delay and all the transformations do not take any time and no dynamics is involved. Next, we will discuss the classification of vector control. So, vector control is classified in the first category. It is direct vector control, or feedback vector control. It was invented by Blaski. And other one is the indirect vector control, or feed forward vector control. It was invented by Hasse. So, this direct vector control and indirect vector control, the method of generating the unit vector is different. They differ in the method of generating unit vector is different in direct vector control and indirect vector control. Then other classification we have rotor flux orientation, stator flux orientation, and air gap flux orientation. So, because vector control means aligning the flux component of the current IDS along the flux, along which flux it is aligned. So, in rotor flux current, rotor flux orientation, the flux component of the current IDS is aligned along rotor flux, hence the name is rotor flux orientation, rotor flux psi r hat. In stator flux orientation, the flux component of the current IDS is aligned along stator flux, which is psi s hat. In air gap flux orientation, the flux component of the current IDS is aligned along air gap flux psi m. So, out of these three, the rotor flux orientation is mostly preferred because it is simple and gives decoupling of IDS and IQS, flux and torque, gives decoupling without any additional network. Whereas the other two methods, stator flux orientation and air gap flux orientation, they are more difficult to implement and decoupling is not straightforward, and so additional decoupling network is used there to give the decoupling. And this decoupling means decoupling of the flux and torque. So, the decoupling means essentially decoupling or vector control it ensures IDS along the flux. Flux means it can be psi r or psi s or psi m. In rotor flux orientation, stator flux orientation and air gap flux orientation in that. So, along the flux, and IQS is oriented orthogonal to IDS. So, that means the psi q is 0, psi q equal to 0 and psi d equals to psi. For example, in rotor flux orientation, psi d r equals to psi r and psi q r equals to 0 in rotor flux orientation. In stator flux orientation, psi d s equals to psi s and psi q s is 0. There is no flux along the q axis. This is the stator flux orientation. And in air gap flux orientation, psi d m equal to psi m and psi q m equal to 0. No flux along the quadrature axis. This is the air gap flux orientation. So, that in rotor flux orientation, psi d r, psi r is a function of only IDS only, not dependent on QS. In stator flux orientation, psi s is a function of IDS only, independent of IQS, and in air gap flux orientation, psi m is a function of IDS, independent of IQs. This is the essential of vector control. Thank you for attention.